Hello everybody, welcome back to the Gregorius Maths video. Apologies for the lack of Theorem of the Week last week. I had another video planned, but unfortunately it didn't materialise. But you know, I'm back with Theorem of the Week for this week, and thankfully for you it's a good one, because it is the 5/8 theorem, which is a neat little result in group theory, which is often overlooked, but it's, you know, very nice, so I thought I'd share it. And actually the idea was suggested by Entropy, so shout out to you for suggesting the idea. And you know, when I heard the suggestion, I knew it was the right one, because it's a nice little theorem, and I thought, you know, it has a nice, neat little proof, so why not share it? Now, what it says is that if we're given two elements of some group G. Now, okay, so we're given G and H in G. If the probability that they commute is greater than 5/8, then G is abelian. So if I tell you the probability that G and H commutes is 63%, then I can tell you for sure your group is abelian. Sorry, that makes no sense, but okay. If it's greater than 5/8, it's abelian. Now, I'm going to split the proof into two parts. Firstly, I'm going to look at how big the centre of a non-abelian group can possibly be. And then secondly, I'm going to take a look at the centralizer of some element of a non-abelian group and look at how big that can possibly be. And then when we combine the two, we can obtain, hopefully, 5/8 as the greatest possible probability given in a non-abelian group. So, let's go ahead and prove this. Firstly, let's look at the centre. Now, the centre of a group, we'll call it Z, for Zentrum. That is obviously a subgroup of G, and so the order of G divided by the order of Z is obviously an integer. Now, because we want the centre to be as big as possible, we want this to be as small as possible, and therefore, we want this to be as small as possible. Now, of course, when this is equal to 1, then the centre is precisely the group, which would mean that the group is abelian. When this is 1/2, when this is 2, when the order of this is 2, this would mean that the order of G mod Z is equal to 2, which would therefore imply that G mod Z is equal to the integers mod 2, because this is the only group of order 2. However, this is bad because it is generated by a single element, and therefore we would just have our group G with just some element that's not in the centre, and the rest of generated by some element that's not in the centre, and then the rest of the elements will be in the centre. That's obviously bad, because then obviously that by definition has to commute with the elements of the centre, so we get a contradiction basically. And of course we can make similar reasoning when this is equal to 3, because the only such group would be the integers mod 3, and of course this is still generated by one element, so we'd have that this quotient is generated by one element, and the rest of the elements are in the centre, and so because by definition all elements of the centre commute with all the other elements, it's a contradiction basically. However, the good news is there's some hope when the order of this is 4, because then we have a candidate where this group is not just generated by one element, but it could be generated by 2 elements. And that is much better, because now that this is generated by 2 elements, those 2 elements, even though this is an abelian group, even though in the quotient they commute, they need not necessarily commute in the original group G. So I'll give you an example of this actually. I'll give you an example of such a group. I'll give you an example of such a group. So the Quarternion group. So this is a group with 8 elements. We'll call it Q. Plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And it's given by the following set of rules. I squared equals k squared equals j squared equals minus 1. And here we go now. Here we go. Sorry. Let me go in. Ij is equal to k. Ji is equal to negative k. Jk is equal to I. Kj is equal to minus I. Ik is equal to j. Ki is equal to minus j. And minus 1 squared is equal to 1. Sorry, is equal to 1. Now, what's the center of this group? Well, one can easily see that the center of Q is precisely just plus or minus 1. Okay, you can just see that the only 2 elements which commute with everybody are plus or minus 1. So, let's do Q mod Z. So Q mod Z, what does this group look like? Well, Q mod Z is equal to, so we've modded out basically negatives. So now we're just left with 1ijk. So we've got 1ijk. And what do these rules become? Well, these rules now become, instead of minus 1, we get I squared equals j squared equals k squared equals positive 1. We also get now that ij is equal to k, ij is equal to k still. But now, because we've modded out the negative stuff, ji is also equal to k. Okay, now we have jk is equal to I, but now kj is equal to minus I, and so on and so forth. So we have ik is equal to j, and ki is equal to j. So, this group does not commute, which we can clearly see. However, when we modded it out by the center, we got an Abelian group of order 4, i.e. this Quarternion group mod out negatives. And so this is an example, and of course we saw that this fraction could not be 2 or 3, and so the lowest number this could be is 4. So we'll write that down. 4 is less than or equal to G mod Z. And so, what does that really mean? Well, that means that the biggest that the center can possibly be is 1 over 4. So we'll write that down here in green. Let's take stock. The biggest possible center of a non-Abelian group is 1/4 of the group. E.G Quarternion group. Okay, so that's the first part of the proof, and I'll take stock in green in this corner here. Now, the second part is to see how big the centralizer can be. Now, recall that the centralizer is the set of all, the centralizer of G is the set of all elements, let's call them H, in G, such that GH equals HG. Right, so it's the set of all elements that commute with G. So, what do we want to ask? Well, we want to ask, what is the maximum probability in a non-Abelian group that just some arbitrary element G, when we pick it out, that I'm messing up my words. What is the biggest centralizer we can possibly get? So what fraction of the group satisfies this? Now, of course, if the whole group satisfies this, well then okay, it's a commutative group. So the next best option is because we know that the centralizer of just as before, we know that the order of G divided by the order of the centralizer of G will be in the integers, and we know that it's not equal to 1, so the next best bet is that it's equal to 2. And actually this is possible, which we see in the Quarternion group over here with the element I, for example. The centralizer of I is equal to 1, obviously, minus 1, obviously, but also I commutes with itself, and minus I commutes with itself. And this is half of the group. This is 1/2 of the group. And so this can be 2. And so, we found the minimum for this, which is the biggest possible centralizer that we can have. We found the minimum for this, which is the biggest possible center we have. Now all we need to do, let me just take stock of this down here. Biggest possible centralizer in a non-Abelian group is 1/2 of the group. So now all we need to do is assemble this information. These 2 points here, which I've hopefully explained nice and concisely, these 2 points here, we need to assemble them into one probability. So let's take some element G. Now the chances that it commutes, the chances that this element G commutes with some other arbitrary element H can be given as follows. Well, the chances that it's in the centralizer is 1/4. So automatically we have 1/4 times by 1s, because if it's in the centralizer, then it 100% will, if it's in the centralizer, it 100% will, you know what, let me just draw a probability tree. Actually, no, that's complicated. No, it's 1/4 times 1, because this is the chance that it's in the centralizer, and if it's the centralizer, this 1 here comes from the fact that it 100% will commute. Plus, well, if it's not in the centralizer, that's 3/4, times, well, what's the biggest possible, here's where this piece of information here comes in, because when it's not in the center, we have that the biggest possible centralizer is 1/2. Given that G is not in the center, the biggest probability here is 1/2. And so this is maximizing it. So times 1/2. And if I can hopefully do addition correctly, this should give me 5/8. So this is 1/4 plus 3/8, which is equal to 2/8 plus 3/8, which is equal to 5/8, as required. Yes! Okay, nice. So, what have we done? Well, we've shown... Also, I guess if we're getting a bit philosophical about things, we could say perhaps that the Quarternion group, which I defined over here, is the most commutative non-Abelian group possible. Because if we look at it, well, the centralizer of I, for example, is a half, and it's got the biggest possible centre that a non-Abelian group can have. So really this is pretty much the most commutative non-Abelian group you're going to get. And yeah, so we split it up nicely into parts, and hopefully this makes up for the lack of theorem of the week last week. Yeah, thank you, and good day, or good evening, or good morning.